Yeah, thanks everyone for joining our talk. So this will be a pretty demo-heavy talk. Timo will run the demo. I'll give a little bit of introduction and uh, summarize it afterwards. Yeah, so let's get started. The talk is called Flink SQL in 2020. It's been almost 4 years since we started adding SQL support to Apache Flink. The first version that had SQL support was Flink 1.1 back in 2016. And since then, we made significant progress. Today, development is going even faster than ever. New features are proposed and completed at a very high pace. So constantly somebody brings up new discussion on the mailing list of a new feature to add. And recent releases they're pretty heavy on adding new SQL features. Right now, there's like 25 open flips being discussed or being worked on. So this is like one of the most active areas in Apache Flink. Also, we're gaining many more users these days. So this is pretty obvious by just looking at what kind of questions are being posted to the user mailing list. So since all this time, Flink SQL's value proposition hasn't really changed. So we always wanted to build a standard compliant SQL service that's able to run queries on static and streaming data with the same semantics and same syntax. So that's basically what Flink SQL is all about from my point of view. And since this talk will be pretty heavy on the streaming SQL side, I'll just give a quick summary or recap what streaming SQL or what running SQL queries on streaming data sources actually means. So if you think about it, basically all tables that are being processed with SQL queries today are somehow changing over time. So either you have a table that is changed by transactions of coming from some business applications, or you have more analytical tables that are being extended by ETL processes. So somehow the data that is being processed by SQL queries is changing all the time. However, what traditional query processors and database systems do is when they run a SQL query, they conceptually take a static snapshot of the table, a consistent view of the data at the point in time when the query was started. So at that point, the input of the query is finite because they just take this static snapshot of what the data was at that point in time. The query processes this data, and then the result of the query is also finite, and you also have a definitive answer for what was in the about the data that you processed. However, streaming SQL processors work a little bit different because they start continuous queries over changing or dynamic tables. In Flink SQL, we call them dynamic tables. This basically means that the input to a query is unbounded, so you'll get more and more data. It never stops. You're just getting the changes of your table being fed into the query, and then the query computes the result based on all the changes that it has seen so far. This means that the query result is never final. It needs to be continuously updated as the query sees more and more data, and it might also be potentially unbounded. That kind of like depends on what changes are coming into the table and also what kind of computation the query performs. However, something that's important to note is that the semantic of a query is the same, or at least in Flink is the same, regardless whether it is executed on a snapshot of a table or on a continuously changing table. So basically, when you have a certain query, you can run it on either a static snapshot or on a table that is evolving, that is dynamic. To make the point a little bit more clear, I have some simple animation here. So imagine you have a table that consists of 3 rows: a user field, a click time field, ctime called here, and some URL. And this query or this table is now being written to by some kind of external process. So this process adds 1 row for user Mary. It adds another one for Bob. It adds another one again for Mary. And then at some point in time, we want to analyze the data in this table. So we submit a SQL query. Here, the query is very simple. We just want to know how often the user clicked on some URL. So it's a simple select user count from group by query. So when we submit this query to a traditional database, the database would basically take a consistent snapshot of the table at that point in time. And then if then later some row is added after the query was started, then this row is not considered. Instead, the query will only be computed over the first 3 rows in this case. So then the query computes a result, and this result is final because all the query was meant to do is to compute a result for these first 3 rows, right? So that's pretty straightforward. If we have a table that is, or if we have a query that is being run over a continuously evolving table, then it looks a little bit different. So again, we have the same table, but now we want to, we submit the query, for instance, right in the beginning. And the query now will listen to changes on this table. So if now some kind of external process or a stream or whatever feeds data into this table, then the query will receive this change as it happens, and then continuously update its result. So in this case, it just emits, it updates the result table from being empty to have a single record with the user Mary and account 1. And as more and more data is added to the source table, the query automatically updates the result table. And at this point in time, the input table contains exactly the same data as in our previous example, and also the result is exactly the same. However, if now 1 more row is added, the query will automatically update also the result table. So that's basically all that's, or the most important point to know about streaming SQL is that it's actually not that much different from traditional SQL. It's basically just having a continuous query, listening to changes on a table, and then dynamically updating the result or adjusting the result depending on how the input table changed. So what will we show in this demo, or what will Timo show in this demo? Obviously, we want to show some of the most exciting features that were recently added. For that, we'll use Flink SQL to read and write data from different storage systems, such as Apache Kafka, MySQL. This is going over a generic JDBC connector, so you can basically replace MySQL by any other database with a JDBC connector, and also some S3 compatible storage. We'll show how you can manage catalog metadata with Apache Flink. This was something that was a little bit or not really possible a while back. So we'll show you how you can create, alter, drop tables and views with the DDL statements, and also how to store this metadata persistently in Apache Hive's metastore catalog. We'll also show some examples of how Flink unifies batch and stream processing, basically running the same query on a static data set and on a streaming table. And also show how you can use Flink to maintain results of continuous queries in Kafka or MySQL. This is something that has been basically this is a feature that has gotten quite a bit of attention quite recently, also being named like as view maintenance, or maintaining views of computed data in external systems. So how does our demo environment look like? So we have this set up in a Docker Compose environment with quite a bunch of containers. So in top, you basically see we have 3 Flink containers. There's, of course, a job manager and a task manager, which basically make up the computation part of the Flink cluster. There's a container for the SQL client that is also shipped with Apache Flink, and that you can just get from Flink's distribution. The Flink client is also connected to a container running Hive Metastore catalog. So we'll write and read some catalog metadata to Hive Metastore there. And then there is a bunch of systems that we read and write data from and to. So first of all, there's an Apache Kafka cluster where we have one additional container pushing some data into the Kafka topics. So the Kafka topics are being fed where the demo is running, so they're not pre-populated, but instead we push the data there more or less in real time to the Kafka topics. There is a container running MySQL and also another container running MinIO, which is an S3 compatible storage system. The scenario that we're showing is an order system, which we derived from the well-known TPCH benchmark. So if you're familiar with that one, you'll find most of the relations look quite familiar. So the central entity in this model is an order, where one row in the orders table corresponds to one order. Each order has multiple line items, and an order also, of course, belongs to one customer. The customer is located in a nation, and each nation belongs to a region. And all of these relations can be joined with each other. So all these region, nation, customer, orders, and line item are pretty much derived from the TPCH benchmark. We did some smaller modifications to the data. For instance, we changed order date by order time. So instead of having a date here, we have a more fine-grained timestamp, basically simulating that orders are coming much faster than before. And then we also added a rates table, which is a table that has exchange rates for currencies. So line items also have have a currency field, and this currency field can then be joined against the rates table that basically returns the current exchange rate to euros. The top 3 tables here, orders, line item, and rates history. These are tables that are frequently changing and are being backed by Apache Kafka. And the lower 4 tables, region, nation, customer, and rates table, we put them in MySQL because they are not updated that often. And we also kind of want to show that you can basically work with these tables even though they are stored in different systems. All right, and at this point I'm handing over to Timo, who will run you through the demo.
Thank you very much. So first of all, this is a live demo. It's not a recorded video, so let's cross fingers that everything works. So as Fabian said, we have a Docker container. Let me quickly run this Docker container. As you can see, we have a lot of systems involved. We are starting these systems now. Let me start first into look into some of those systems. So for example, we could just run and look into the Kafka container a little bit, in this case into the orders table. We are running the Kafka console consumer. And you can see here is the orders data coming in. Let's cancel it again. Let's also quickly take a look into the MySQL. container. So as you can see, we have 4 static tables in MySQL. You can also describe it here a little bit. So like this is a typical customer, for example. And typical customer, for example, looks like this. So typical relational data. As Fabian mentioned, we also have an S3 storage, or we have a mock of a S3 storage. Right now, this S3 storage is completely empty. We have a running Flink cluster, and as you can see, we have not executed any job so far. So let's get started with the
Timo,
demo.
can you make the font a little bit larger in the console? People ask to make it a bit larger.
Is this better here or even larger? Yeah, I'm running out of space, but I will try my best. Maybe this size. Yeah. So so let's start with the SQL client. Yeah, as Fabian mentioned, we have a Hive catalog. The Hive catalog in this example stores most or all of the static tables, which are backed by MySQL. And we also have like a built-in default catalog, which stores the Kafka tables. So you don't necessarily need a catalog to get started. And in this case, we have the line items, the orders, and the rates, history, Kafka topics in the default catalog. We can also describe some of those tables in the SQL client. Here you can see the schema of the orders table. We can also use the SQL client to get an insight into the Kafka topic. In the background, we will submit a job to the Flink UI, and then we will see how the results of the Kafka topic are streamed into the SQL client. We can also explore some rows, open some of the data if we want to. So let's start with using our Hive catalog. It's a simple command. We just call use catalog Hive. And as you can see, once we execute the show tables command again, we will see a different set of tables. This time, the static MySQL tables. Again, we can describe them, like nation looks like this, for example. And also, same as Kafka, we can take a look into our MySQL tables, get an insight there in a streaming fashion. So let's actually run some real serious queries on the static and dynamic tables. As Fabian said, like Flink SQL tries to or aims to unify batch and stream processing. So many queries can be executed on static and on dynamic tables. Maybe we just start with taking some snapshot of our production data in Kafka, because it also allows us to show how the DDL in Flink SQL looks like. So this is a typical DDL. In this case, we are creating a table dev orders. The table has a schema part, which configures the schema of the table and also some constraints. And it has a with part, which configures the properties, how to connect to an external system. So in this case, what we want to do is we want to take a snapshot of our production orders. We want to dump this snapshot into our S3 file system in a regular CSV format. So the first columns here are regular SQL. The specialty here is that we are also need to define some watermarking strategy. This allows us to also do event time computations on our data later. So let's just fire this snapshotting query, if you want to call it like this. So what we are doing is we are reading from our production orders and insert into our dev orders CSV file. We can go into the Flink UI now, and as you can see, there is a running job. Nothing special, it's just dumping from one system to the other system. We are just sampling some data into this CSV file, so I can also cancel the job now. And as you can see, like now content of the Kafka topic is part of our S3 bucket. We can now also look into what we just wrote into S3. Let's take a quick look. Yeah, and as you can see in the left corner, the table program finished because it's not a Kafka topic anymore. We just scanned through the data. We have 50 pages of this data. We can also perform now some computations over the data, like a simple count of all orders in the CSV file. Yeah, here you can see the count. Yeah, so far we executed this query in the streaming execution mode, but especially if you work on bounded data, it might be more efficient to use the batch mode, so the batch engine for efficiency, because certain algorithms, if they know that they can execute it on finite data, we can further optimize the runtime. So we are changing to the batch execution mode now. Let's have some simple typical SQL query here. So what are we doing? We are scanning over the dev orders, and we are rounding or rounding up the order time to minutes. So we are basically computing a window of a minute, and per minute we are computing the sum for revenue, and we are counting how many orders are included. You can also run this. And here you can see the result of our batch computation. As you can see, the query is basically the same for batch and streaming. We can switch back to the streaming mode, and we can execute exactly the same query again with exactly the same result. The difference here is how is it actually executed under the hood. I will show you some internal feature of the SQL client, because you can actually interpret this whole table, or you can visualize the table also as a changelog. So what is actually happening under the hood when you're executing this query? What you can see is that actually updates are traveling through the system. So you have insertions and deletions of rows. This is because you have count and sum, and so you have aggregations that need to be updated. So whenever a new row comes in, you need to update your output. This works in batch and in streaming, but especially in streaming, what you actually want to do is you want to keep the state size small. So you don't want to keep the counts and the sums forever. So we can actually streamify this whole computation a little bit to make it more efficient in a streaming production use case. So first of all, we are going back to our result mode table. And the same query as above, using some built-in functions from Flink, can also be expressed here as this query. We are using a tumble function based on the time attribute order time and an interval of 1 minute per tumbling window. It computes exactly the same result as before. The difference now is if we go into the changelog mode, we will see that, let me show it. will see that the changelog under the hood contains only insertions. So it only emits results once the 1 minute window has completed, thanks to event time and watermarks under the hood. So let's also maybe do a bit more complicated streaming queries. One of the most complicated but also most useful operations in databases is usually joining tables. And Flink knows roughly 5 different ways of joining tables. Each join is useful for a specific kind of use case. Let's start with a regular batch join, basically. So I switch to the execution mode in batch. And I run the following query. So that could be a typical like day reporting query in batch. What we're doing here is we're basically showing the customers and their orders by region and priority for a specific day. So in this case, we're selecting the 1st of April. And what this query basically does is we are joining the snapshot of the orders table with the customers, nation, and region. So you can see under the hood, we are reading some data from CSV. We are reading some data from MySQL. And yeah, here you can see the result. So that's a regular join on static tables. So let's go back to streaming and let's execute some joining on more dynamic tables, on streaming tables. First of all, we can run the same query that we executed before on some streaming data. So let me copy this over. So it's basically the same query as before. The difference is that I don't read from the dev orders anymore, but I read now from the Kafka production orders topic. And you can see how the join is executed in a streaming fashion. It's not ending and it's continuously updating. However, there are some notable properties of this join. So first of all, what is the difference between batch and streaming tables? Batch tables can be read just once. There are no updates that need to be considered. However, for streaming, I mean, if you know the semantics of a regular join, you know that all input tables can change at any time, but that is not very beneficial for streaming use cases, because in streaming use cases, that would mean we need to materialize all input tables in state, which means that at some point we would grow out of memory in Flink. That's why Flink has special, more streaming-like join optimizations. Let me switch back to the other catalog. This is how a typical interval join looks in Flink. So we are basically using or leveraging the time attribute of the streaming tables, and we are telling the system, hey, the line item order time must be between some range of the orders order time. So that means we only need to keep, in this case, 5 minutes in state, and after that we can be sure that there are no tables later, no rows coming in later, so we can discard the state that is required for the join. So we have some different properties. We have event time, semantics, and small state size in this case. Sometimes you also want to join streaming and batch data. Let's assume we want to join some records from our Kafka topic with records that are stored in MySQL. So Flink provides an enrichment join in this case, a streaming enrichment join, which looks up in the MySQL database. We are using the system time as of SQL standard for that. It basically means we are for every row we are performing in processing time. We are performing a lookup in the external system for the given key. Yeah, in this example, we have our production line item table, and we have currency, and we want to look up the current exchange rate in our exchange rate table in MySQL. And here you can see for each currency, we are looking up the current exchange rate in real time. Yeah, so I mean, this works. So whenever we, for example, go to MySQL, we can also maybe change some of these rates. So here is the rates table in MySQL. So now we updated, for example, one rate for US dollar, and yeah, if we would run the query again, then the result of the lookup would show a different result. Yeah, so the properties of this join are basically we have processing time semantics. Rates are looked up from MySQL when they are needed, and the MySQL table can be updated while the join is basically running. So, but sometimes what users actually want to have, they want to connect the rate at the time of the row. So, I mean, the rates are continuously changing, and if you want to compute the exact amount or the exact conversion rate, actually you need to look at the table, at the rates table at a given point in time. And Flink offers you this functionality. We are calling this temporal tables. The syntax looks a bit different here. So we are using a table function that we have registered before. We are passing into this table function the time of the production line item. And that means the system will give us the content of this table for this key at the given point in time. So that means in this case, we have event time semantics. And when we also execute that, the rates changes as the records are produced in Kafka. Yeah, because of time constraints, I cannot explain it further, but there is also a lot of documentation online about this. Okay, so much about joining. I also want to quickly show you a different feature that makes Flink pretty unique. Maybe some of you have already heard of the match recognize clause. It was recently added to the SQL standard in 2016. And what the match recognize clause allows you is basically performing pattern matching or complex event processing on tables. And Flink has added support for that a couple of months ago. And I quickly want to show you a bit more complicated example how a match recognize query looks like. So what I basically want to do is I want to find customers that have changed their delivery behavior. I want to search for a pattern where customers basically changed their shipping shipping strategies. So instead of paying in advance, they only want to pay on delivery or collect on delivery. For that, I first of all need to provide a helper view. Because our line item has no customer key. So I need to join the line items with the production orders to get a customer key. So I call this view line item with customer. So after that, I can now execute my match recognize query. I will not go into the details how the clause works, but roughly, as you can see, we are using match recognize here. We are partitioning by customer. We are ordering by time. We are measuring certain results once we have found a pattern. We are defining the pattern here. In this case, the pattern means we are waiting for at least 5 other events, and then we are waiting for the COD event. And the events are basically, or the patterns are basically defined here. And we can also run this. Oh, there was a typo. And you can see some customers are recognized that have changed their ordering behavior, but just 3 of them right now. So as a last topic, I mean, we are also running out of time, but of course it is also possible to dump results from one system to the other. So let me quickly, for example, show you how we can create like materialized views in Flink SQL. So first of all, like I'm creating a helper table, which I call minute statistics. I want to dump these statistics into Kafka in a JSON format. The topic is automatically created, and I'm just using one of the queries that we are created before. So I can say insert into minute statistics, and I insert my time window computations there. I can submit that. It's submitted to Flink, and we can also see that in Kafka if we want to. That's not Kafka. You can see here's our JSON data that is written out into Kafka. And to complete the story, we showed a lot of streaming queries. We can also do the same in Hive fashion. So we can create a new table in MySQL. Let's go to MySQL. We are creating a new table in MySQL. We are calling it region stats. Then we are registering this table in Flink's catalog, or in the Hive catalog in this case. So region stats, we're using the JDBC connector. And again, we can dump the result into MySQL. So in this case, yeah, we are using the join result from before for some region stats, and entering them into MySQL using the insert into statement. As you can see here, we also configured the flushing behavior. So in this case, we will flush every 2 seconds, or if we have 1,000 rows, we will flush the result into MySQL. And we can also show how the table updates. So if I re-execute, you can see that some results here are changing. So much from my demo. Back to Fabian.
All right, yeah. Thanks, Timo. 1 second, let me continue. Oh. Can you see the slides again?
Yes.
Okay, great. All right, yeah. So what is currently possible in Flink 110? So we're seeing most of these, what is listed here. So there's obviously support for very simple select from where group by queries. You can do different kinds of joins. We didn't show Flink support for user-defined functions here. So you can have different types of UDFs being implemented in Java or Scala and registered there. Support for Python UDFs is also on the way. So you can have Scala functions, aggregation functions, or table-valued functions. There is support for over and window clauses in streaming SQL. We've seen the time version table joins and lookup table joins and recognize clause here. Something that's worth noticing is that even though we didn't really show it here in this demo, Flink is a very capable batch query processor as well. Since this version, due to the integration of the Blink query planner, Flink now has full support for TPCDS queries, which is TPCDS is another well-known benchmark for decision support queries. So what's coming next in the next Flink version? Or at least what's planned for the next Flink version? Wait a second. Slide is not advancing. So something that is that's coming in Flink 1 and Flink 111 are more DDL statements. So you can create temporary tables and views, as well as creating databases and also show database statements. So more control via command line lines, like the one that we have shown here. We are extending the set of built-in functions now to also support the JSON functions that were also recently added to the SQL standard. So with these functions, you'll be able to inspect, query, and modify JSON data that is stored in text fields. There is also currently in the workings is a shortcut for DDL. So in case you're creating many similar tables with a similar schema, you can just use the like clause to basically just extend a base table and derive a table from it, just changing a few properties. So that's very convenient. And then finally, there's another change that I'm very excited about, is the support for changelog processing. So basically being able to ingest changelog streams into Flink and then building up internally a dynamic table from these changelogs. This comes with new interfaces for table sources and sinks, and also with a deep integration with the Kafka connector, and an implementation for the Debezium format, which is a fairly popular format to encode CDC change data capture streams. So for instance, there's tools that extract the changelog stream of a Postgres table into Debezium, and then with that you could basically extract the changelog from Postgres into a Kafka topic, and then ingest this changelog into Flink, and then internally rebuild the Kafka, the table in Postgres, and then run continuous queries over this table as it is changed from the changelog stream, which of course is fed by the changes on the Postgres table. So you could have an application changing the Postgres table and then seeing the result of analytics later in your Flink as the result on your Flink query. All right. So much for our talk. We went a little bit over time, but since this is the last talk of the day, I hope you stick with us for the 7 more minutes that we've taken. Yeah. So to summarize, Flink SQL made huge progress in the last year. Many more things to come. Flink is now able to connect to many systems, file systems, relational database systems, log systems like Kafka, and we're running queries at very large scale on static and dynamic data. And if you need something like that, yeah, please try it out.